We all have learned it in school. Planets orbit the Sun in the shape of an ellipse. This is known as Kepler's first law, and it is older than Newton's law of gravitation. Kepler observed something he just couldn't explain, and only thanks to Newton's work his observations finally made sense. And for those of you who have always wondered, just like me, how to mathematically prove Kepler's first law, this video is just for you. So let's go. First of all, we have to take a look at the mathematical definition of an ellipse. After we have done that, we will switch to the physics side and calculate the conserved quantities of the planet-Sun system, which are just the total energy and the angular momentum. This way we can determine the orbit of a planet around the Sun. We will get an integral which we will have to solve using some cool tricks like substitution or completing the square. And what we will get is an equation for the orbit of a planet around the Sun, which will equal the equation for an ellipse we derived in the first section. An ellipse is pretty similar to a circle, just a little deformed. The two focal points of an ellipse would join to one focal point for a circle. There are many ways to describe an ellipse mathematically, and the most common way is to use the semi-axes, namely the major semi-axis A and the minor semi-axis B. This way, the definition equation of an ellipse looks quite similar to that of a circle. One can also use other parameters, like the semi-lattice rectum P, for example, in combination with the eccentricity epsilon. The eccentricity is defined as the quotient of C and the major semi-axis A, where C is the distance between the center of the ellipse to one of the focal points. Together with P and epsilon, we are able to express an ellipse in polar coordinates, which will come in handy later. So this last equation for an ellipse is the one we are working with in this video. Let me know in the comments if you want to see a derivation of this equation of this polar form of an ellipse. We start with Newton's famous gravitational law and write down the energy of the Sun-planet system. This is only one part of the total energy, namely the potential energy, since it is only dependent on the distance r between the two celestial bodies. The capital M stands for the mass of the Sun, the small m is the mass of the planet, and the capital G is the gravitational constant. Now that we know the potential energy of the system, we can go on to the kinetic energy. We are interested in the kinetic energy of the planet and neglecting the small movement of the Sun. The kinetic energy is just the half of the mass times the velocity squared. But the planet is not moving in a straight line, so we have to treat this velocity as a vector. We have to split his velocity vector up into its x and y component. There is no z component because the orbit completely happens in the xy plane, and this is due to the conservation of angular momentum. Together with the gravitational energy from just a moment ago, we now know the total energy of the planet-Sun system. But this expression for the energy does not come very handy. And since we're dealing with a circular motion problem, it is always a nice idea to introduce polar coordinates. In polar coordinates, x would be expressed as the distance r between the center and the point on the curve times the cosine of the angle phi, and y would be r times the sine of phi. But our formula for the energy contains time derivatives of the Cartesian coordinates x and y, so we need to take the time derivative of those polar expressions for x and y. Both r and phi are time dependent, so we have to apply the product and the chain rule to take the derivative of x and y with respect to the time t. This will eventually give us r dot times cosine of phi minus r phi dot times sine of phi for the time derivative of x, and r dot sine phi plus r phi dot times the cosine of phi for y dot. And now we put those expressions for x dot and y dot into our formula for the energy. But as we can see, we first have to square both expressions. By squaring x dot, we will get r dot squared times the cosine squared of phi minus 2r r dot phi dot sine of phi cosine of phi plus r squared phi dot squared times the sine squared of phi. And similar to that, we square y dot and get r dot squared times sine squared of phi plus 2r r dot phi dot sine phi cosine phi plus r squared phi dot squared times the cosine squared of phi. And this already looks like there's going to cancel some things out when we add x dot squared and y dot squared together. So let's look at what will cancel out. Let's write the x dot squared plus y dot squared a bit clearer. This way we can already see that the two terms in the middle cancel each other out. For the rest, we have to remember the coolest trigonometric identity ever, which is that the cosine squared plus the sine squared equals 1. This way r dot squared cosine squared plus r dot squared sine squared is just equal to r dot squared. And in a similar manner, we can construct the remaining two terms. This eventually gives us r dot squared plus r squared phi dot squared for the sum of x dot squared and y dot squared. And now we finally have a beautiful polar coordinate expression for the total energy of the planet-Sun system. We are ready to tackle the angular momentum. The angular momentum is a vector, and since it is also a conserved quantity, the vector always shows into the same direction. This is why the movement of the planet around the Sun lies in a plane and does not wiggle around. The angular momentum itself is defined as the cross product of the position vector and the momentum vector. And since the momentum vector is just the mass times the speed, we can extract the scalar mass out of the cross product. Explicitly written with the set and set dot component being set to 0, this cross product does not look so scary anymore. All we have to do now is actually calculate the cross product. And through some magic, the x and y component vanish and are 0. Only the z component remains. So eventually we can write the angular momentum of our system as the mass times, in brackets, xy dot minus yx dot, and the whole thing times the unit vector in z direction. Now we just have to write that expression in polar coordinates. Easy thing. Luckily, we have already calculated the polar expressions for x dot and y dot a couple of moments ago, so we can just plug them into the Cartesian formula for the angular momentum. This gives us this very long expression, and either you're a genius and see it instantly, or you take a piece of paper like me and confirm it, but in the end, the angular momentum in polar coordinates will be the mass times r squared times phi dot times the unit vector in z direction. We can write the scalar part of the angular momentum as L without an arrow. This scalar L is constant for the whole period of the planet moving around the Sun. So we can treat this L like a constant similar to the energy or the gravitational constant. This way we can rewrite the angular momentum to get an expression for phi dot. And this expression will help us to simplify the energy in a couple of moments. It also gives us a differential equation for the time development of the angle phi. In this differential equation, r is the only thing depending on time. So we have to investigate this part a little bit further, and we do so with the help of the total energy. With the help of the angular momentum, we will get rid of the phi dot in the polar expression of the total energy. For phi dot, we plug in L over mr squared, which gives us a beautiful expression for the energy, only depending on the distance of the celestial body from the Sun. So how far a planet is away from the Sun is the only thing that determines how much energy it has. All the rest is just constant terms. Now we take this expression and rearrange the terms, such that we get an expression for the time derivative of the distance. Remember, we wanted to investigate this part a bit further. This eventually shows us that the radial velocity squared of a body orbiting the Sun is equal to 2 over m times, in brackets, the energy minus L squared over 2mr squared plus small m times capital M times g over r. Now all we have to do is take the square root on both sides and rearrange the terms to get an expression for dt. Why would we want an expression for dt, you might ask? Well, we can plug this dt into our expression for phi dot and get an integral dependent on r, which will give us the orbit equation of the planet around the Sun. You will see what I mean in a second. So we rewrite the differential equation for phi dot such that we have an expression only for d phi. And then we plug in our expression for dt, which we calculated just a second ago. This gives us this monster-looking expression for d phi containing all types of letters. The last step is to integrate both sides. Integrating the left side is easy, this just gives us phi. Integrating the right side is a bit tricky, and this is the mission of the final section of this video: solving the integral and reaching the trophy of Kepler's first law. Solving this integral will tell us the connection between the distance r and the angle phi, which is the shape of the planet's orbit around the Sun. The first thing we can do is drag the m as an m squared into the square root. After we have done this, it is time for the first substitution. The idea is to substitute 1 over r with xi. The derivative of xi with respect to r would be minus 1 over r squared, which is just xi squared. So the transformed infinitesimal element of the integral is minus d xi over xi squared. And plugging this substitution in, we get a minus sign in front of the integral. The xi squared over xi squared in the numerator of the integrand cancel each other out to 1, so only L as a constant remains in the numerator and we can extract it as a constant out of the integral. Now we can abbreviate the integrand by defining some constants. We define a to be 2me and b to be 2 times capital M times small m squared times the gravitational constant g. And this way we get minus L times the integral of d xi over the square root of a minus, in brackets, L squared xi squared minus b xi. And this expression in the brackets looks a lot like binomial formula and completing the square. Let's have a closer look at the expression in the brackets. It looks like 2/3 of a binomial formula. We add the final third and subtract it right after to only add 0, and this is completing the square. In our case, we are adding and subtracting b squared over 4l squared. And we can now combine the first 3 terms to the binomial formula and are left with a minus b squared over 4l squared. We now plug this whole expression into the integrand and, well, it looks more complicated than before actually, but bear with me, it's soon gonna look nice. First we combine the b squared over 4l squared with the a, since they are both not dependent on r and therefore constant. And this new constant we redefine for abbreviation as capital A. And then we also perform the next substitution. The whole term inside the brackets now turns into u, and the derivative of u with respect to xi is just the constant angular momentum L. And therefore the infinitesimal element is du over L, and our integral simplifies a lot, as you can see. First of all, the L over L just equals 1. Then we can extract the a as a constant factor out of the square root and the integral to perform another beautiful substitution. And yeah, I know we could have combined some of those substitutions, but for the sake of simplicity I wanted to do it as explicit as possible. So now we substitute with eta being u over the square root of a. The derivative of eta is 1 over the square root of a, and therefore du is the square root of a times d eta. And plugging this into the integral, we get a beautiful expression which we can solve with one last substitution, a trigonometric substitution. The term inside the square root reminds us of the coolest trigonometric identity, so we're substituting eta to be the cosine of some angle theta. This means that the derivative of eta with respect to theta is minus the sine of theta, and therefore d eta is equal to minus sine of theta. Plugging this into the integral, we first can drop the minus sign. Luckily, it was about to make me nervous. And as an integrand, we have sine theta over the square root of 1 minus cosine squared of theta. And 1 minus cosine squared of theta, well, that is of course sine of theta. So we have sine of theta squared, and the square root of that gives us sine of theta. So we have sine of theta over sine of theta, which is just 1, so the integral solution is theta. And this finally is the inverse cosine of eta. And now all we have to do is run back our substitutions and plug in step by step, beginning with eta. First, we plug in u over the square root of capital A for eta. Then we put in the expression for u, which is L xi minus b over 2L, and the one for a, being small a plus b squared over 4L squared. And we already see our solution growing like a tree. Finally, we plug in the expressions for the small a, which is just 2me, and b, which is 2 times the mass of the Sun times the mass of the planet squared times the gravitational constant. And this is how we end up with the final solution. This is our expression for the angle phi dependent on the distance r and a bunch of constants. Now we need to remind ourselves what we actually wanted to achieve. We were aiming at proving that planets orbit the Sun in ellipses. The polar equation for an ellipse only contained the angle phi, the distance r, and some constant parameters p and epsilon. So everything that does not contain an r or a phi gets absorbed into a single constant. We define the whole square root term in the denominator as gamma. Then we solve the equation for L over r. The second term on the right hand side now is constant, so we can absorb it into a parameter we shall call delta. With this we can already see the goal ahead of us. We just have to solve this equation for r. So all we have to do is some rearrangements and we end up with something that looks almost like the formula we want. The term L over delta in the numerator is just a constant factor, so we can absorb it into a redefinition as the parameter p of our ellipse. And the term gamma over delta in the denominator is constant as well, so we will absorb it into the parameter epsilon. And here we are with the orbit solution to our integral, the polar equation of an ellipse. Amazing. This derivation brought so much joy to me when I found it in Lev Landau's Introduction to Theoretical Physics. I just had to share it with you. If you had fun going on this journey with me, please leave a like and maybe consider subscribing to my channel. All of this helps a lot and I know you're hearing it all the time, but yeah, it helps. Very nice. Thanks a lot. If you would like me to continue with derivations for Kepler's other laws, which is a bit simpler than this one is actually quite heavy, let me know in the comments. Yeah, I hope to see you in the next video. Until then, bye my fellow path integrator.